Hello and welcome to day 10 of learning leetcode from chatgpt. So let's get started. So in the last lesson we looked at like recursion, and we looked at the climbing stairs problem, where if I go to the solution, oh no, I don't have it with me. It's just basically Fibonacci, and if it's like equal to 2, no, sorry. Let me just look up because for some reason I'm really low on memory. I think it's because OBS is. Remember that. So I'll go to the solution. Or just hashtag. Please give me the climbing stairs problem. Problem solution. Okay. So it was basically just Fibonacci, and where it was equal to 1, we would just return 1. And if it's equal to 2. No, sorry. I think we just, 2. So solution code. Oh, so here we didn't actually do a loop. We just did current equals first plus second. Well, yeah, this isn't the recursive one. So current equals first plus second, first equals second. Okay, yeah, I'm not sure why I'm doing it this way when it taught us about recursion, but we'll just move on to the next lesson. So lesson 13. Okay, backtracking, sorry. So Sudoku board. Okay, let's see. Please give me lesson 13. So backtracking is an algorithmic technique used to solve problems where multiple solutions or paths exist. It involves exploring possible choices and backtracking when a choice leads to a dead end, thus allowing you to explore another path. This approach is useful in solving complex combinatorial problems such as permutations, combinations, and constraint satisfaction problems. So recursive exploration backtracking often uses recursion to explore choices. Base case, when the goal is achieved, the solution is added to the results. Pruning, cutting off paths that don't meet the problem's constraints to reduce computation. So for example, solving a Sudoku board. Sudoku is a classic example of backtracking. You fill each empty cell with a number that satisfies Sudoku rules. Each row, column, and 3x3 subgrid contains unique letters from 1 to 9. If a cell choice violates the rule, you backtrack and try a different number. So, problems to practice: permutations. So, generate all possible permutations of a given list of numbers. Use recursion to swap elements in the list to generate different orderings. Okay, so permutations. So that's basically every different combination. I'm actually not sure how you would use recursion to swap elements in the list to generate different orderings. Okay, I'm gonna maybe come back to that. So given a partially filled 9x9 Sudoku board, fill in the missing numbers to solve the board. Starting with the first cell, try placing numbers 1 to 9 while checking if they fit constraints, and backtrack if a placement is invalid. So subsets optional. Given a set of numbers, generate all possible subsets. This problem is a subset of backtracking. For each number, decide to include or exclude it. Okay, so I'm going to do the first problem, and I'm going to learn about it, how to do it. So use helper functions to check constraints. Using Sudoku, check if a number is valid for a cell. So we could just do a simple check if the specific column or row has all unique elements. So by practicing these problems, you'll develop skills to tackle complex decision-based problems effectively with backtracking. So also with a Sudoku, we'd have to check every 303 grid. So yeah, I'm actually kind of intrigued of how you would do permutations with recursion. Could you, like, first of all, maybe pass in like every possible position? I don't know. Please give me the solution to this problem. To generate all permutations of a given list, we can use recursive backtracking approach. Each recursive set, we swap elements in the list to create new orders, generate permutations until each position has been fixed once. So to generate all permutations, recursive backtracking, okay. At each recursive step, we swap elements in the list to create new orders. Generating permutations until each position in the list has been fixed once. Okay, so could it be a bit like bubble sort, where we swap every element instead of comparing? We swap. I don't know. So result equals. So we do backtrack 0. So if start is equal to the length of nums, a result dot append nums, append a copy of the current arrangement, and then we return. So we're just storing this right here. Otherwise, we go for every index in the range of the start to the length of elements. So nums at start and nums at I. So we're just swapping these. Backtrack. Yeah, so we are basically doing a bubble sort type thing. Backtrack start plus 1. And then we're going to do nums at start. So we're also going to swap them back after we've done that backtrack, because we're eventually going to reach this subcase. I see. Okay, yeah. So that's that solution. And that's that for this lesson. So thank you for watching, and I'll see you in the next video. Goodbye.